Welcome back. I'm joined by Adam Jones of Crescend and our special guest, Jon Forster. Welcome, both of you. Glad to have you both here and have a conversation today.
Thank you, Lori. Thank you, Adam. Great to be here.
Yeah, thanks for joining, Jon. Thanks, Lori.
Awesome. And Adam, let's start with you. Let's go ahead and, if you wouldn't mind, just giving a brief introduction of who you are and what you do here at Crescend.
Thanks. I'm Adam Jones. I'm a director of sales here at Crescend. I've worked in the microwave industry in a bunch of different markets for majority of my career. I've been with Crescend the last couple of years, helping us grow the solid state product line.
Awesome. And we're joined by Jon Forster, our special guest who brings a lot of research and information about microwave technology, especially in the area of comminution. And Jon, we're so glad to have you here today. Please tell us a little bit about yourself and your background.
Thank you, Lori. So my background is mining engineering and mineral processing. I completed my undergraduate and master's degrees at Queen's University in Kingston, Ontario, Canada. And then I went on to pursue my PhD at the University of Toronto. And my focus of my research was using microwaves for assisted comminution and ore sorting. And since completing this work, I have, been very close with this field. I've been reading a lot of papers, and I'm really excited about, what the future has to offer, especially with regards to solid state.
Thank you, Jon. We're so glad to have you here. And for anyone who's joining in on this this interview, there was a part one where we talked with Jon and then a bit more a high level perspective overview, and now we're going to get a bit more into the details of how to apply microwave technology for mining and comminution. So I guess to kick us off, Adam, can you give us an idea and an update on Crescend's field deployments of solid-state microwave generators and its proven use in mining comminution?
Sure. So to date, Crescend has deployed a bit more than a megawatt worth of power into the field. This is done through our mainly through our combined systems, where we've combined 50 kilowatt generators into 200 kilowatts inside a seagoing container, and then these units had all the utilities configured in them, and so there's 5 of these units out in the field doing work in field style trials and studies. I can say that, I've been on site for a number of these trials, and the customers are the results that these customers are getting in their comminution experiments are beyond their expectations. This is really a testament to some of the power that we were able to deliver, at these focused applicators. And it'd be great to share more details on who, what, where, and and how, and what types of materials they're doing. But as we alluded to in part one, a lot of NDAs are covering this, and the customer is not ready to really release and publicize this too much at this point in time. But hopefully in the near future, we will be talking more about this with the greater community.
Thanks, Adam. And so I'm wondering, beyond comminution, what potential applications do you see for solid-state microwave technology in mining? And I would ask this specifically to Jon, if you have thoughts on that.
I would say there's a few applications that come to mind. Off the top of my head, water removal is an opportunity, but when we say water removal, we have to be careful. There's de-icing, there's drying, and there's also dewatering of material if you're removing the hydroxylated minerals. So starting with de-icing, imagine we have a mine site, it's remote, we have very cold temperatures, and we have our run-of-mine material and it's frozen. It may be possible to irradiate this material and melt the ice and then process that material. So you would need to have minerals that are very microwave responsive. An example could be something with magnetite or ilmenite. Now moving on to drying, so the removal of free water, so water that is completely removed at 100 degrees Celsius. Depending on the application that we're using, this may or may not be competitive. We need to know all the different process variables, but this is something that has been done on nickel laterites. I think it was in Australia. I think I saw a paper about that a few years ago where they're using microwaves for drying. As far as I know, it hasn't been widespread. So the third water removal technique is dehydroxylation. So you can imagine we have bound water in our material and we want to do a dehydroxylation reaction. So it's possible to use microwaves for this. But again, this would require an energy balance. So we have to do the basic economics to look at how much energy we're going to be using for this type of reaction. The second item is reduction. And I have experience with this using carbon and using that as a reducing agent with nickel laterite ore to produce a ferronickel concentrate. And there's also roasting, so heating out material in air. So these are all potential applications that you might see in the future if they don't already exist. And just as a side note, I won't spend much time on this, but using microwaves on the moon. So for irradiating the lunar regolith, if we're just establish infrastructure on the lunar soil, we need to be able to sinter uh, that material. And it's possible to use microwaves because they can pass through the vacuum of space.
I'll add a couple things to that too, Lori. I think that the opportunities in these areas is where you, as John alluded to, is the selectivity capabilities of microwave power. And again, it gets into the economics, but you have to look at this. But the being able to selectively heat water and nothing else in your process is something that's very unique to microwave power. And so you look at that, the energy required, and it's not it's a significant amount of energy required to do this, but you can't break the laws of physics in this regard. But microwave power will selectively heat the water to evaporate it. And it, based on the material and so forth, like John had mentioned, it may not heat the other material and it won't heat the air. You don't need to have a vessel that is hot and that is being that is transferring the energy through conduction or a convection, so you can selectively heat that. And that situation could show a very promising ROI in terms of that. Even considering the penalties of efficiency loss when you have to convert AC to AC or to microwave power. So, John, what do you think the specific attributes of solid state make it an exciting innovation for the industry?
Well, that's a great question. I think the fact that you can combine, feeds into an applicator, to produce up to 600 kilowatts of power with the commercially available waveguide is a significant advantage. Another item I would say is the robustness of solid state. So, if something happens with the equipment and you need to do some maintenance, you can simply swap out that component. Whereas with the magnetron-based system, you have to hire a specialized technician to physically come in, shut down that operation, and then interchange that component.
Do you think the frequency agility or multi-band pieces come into play with solid state?
Yes, so that's another key aspect. With solid state, we can sweep a broader range of the frequency. We can have a better coupling with the material. One thing that I would be interested in seeing operationally regarding the multiple frequency bands is suppose you had both 2450 megahertz and 915 megahertz, uh, both feeding into a single applicator. The reason for this could be suppose in a mining operation you have material feed with variable particle size distribution. It's not always possible to change the feed particle size distribution, but what we could do is change the frequency. So by using microwave pulsing with solid state, you could intermittently go back and forth between the 915 and 2450. And the key idea behind this is matching the penetration depth with that of the size of the material that you're irradiating. So this could not be done with magnetron technology.
Yeah, one thing I'd add to John's power comment is that I agree with him on the 600 kilowatts into a single transmission line. One of the challenges with when you put more than one feed or more than one transmission line into a single applicator, um, solid state is uniquely capable of keeping those feed systems what's called coherently controlled, which means they're coordinated. The energy that goes into that applicator can be assured to be combining in intensity and in field strength. you have a situation with many magnetron-based approaches where if you have multiple feeds coming into your applicator, these systems can be out of phase and be destructive in the energy combination. So you don't realize the full potential of the application power distribution, if you will. So, solid state inherently in its design is phase coherent, and you can coordinate these either coherently or you can selectively shift the uh, the phase and the power and the frequency between the different feed points.
Oh, thank you. And if we could just take a little bit of a pivot and talk a bit about decarbonization for a moment, could solid state technology contribute to decarbonization efforts, specifically within mining industry?
I can go first with this one. So, as I talked about in our last interview, anytime we go to a mining conference, they're always talking about increasing the metal throughput for society to continue to grow, but we also need to reduce our CO2 emissions. So, as long as the energy source is clean and an unit operation that you're operating, you're not off putting any CO2, then most definitely this is going to contribute to the decarbonization efforts. And as a collective community, we have until 2050 to reach net neutrality. Some other companies are targeting this initiative at an earlier date. I think it's just a matter of time before we see that initial installation, and then other companies are going to follow suit.
Yeah. Adam, you have any additional thoughts on sustainability within microwave use for?
Only that in the fact that I think that it's uniquely a electrical process, electrical heating process that has unique characteristics in terms of selectively heating the material. Obviously there's other electrical heating processes, but they don't work the same way as microwave power would, where it's selective in its nature. It's based on the application. Obviously, there's many applications where it may not work, but um, the but that's a good. I think that's a good summary.
Yeah, and specifically, we're talking about depending upon where the energy is sourced. So, what are some of those? Being able to have green energy to source from, or clean energy to source from. What are some of those, specific barriers, and why that is a concern, or could be a barrier to more wider spread adoption of solid state in mining? Can you talk a little bit about some of the logistics that make that a challenge?
As we all know, there's with every mine site, most of them are remote. They have their own power challenges with maintaining a clean site operation, and so adding more microwave power, or sorry, electrical power to the site to run an electrical process may be a challenge. There's significant efforts underway now. In my research that where mine sites are looking to aggressively get greener on their energy source, but the adding more power demand through different processes may be a challenge in adoption.
So I was going to ask you, we have to look at, from a commercial perspective, some of the offsets of that, the benefits. What are some of the benefits of using microwave for mining in these remote locations?
Well, for one thing, I would say that if you have an already existing process, a brownfield site, you can adapt your system and install a microwave system, which might not be possible with other unit operations that has a much lower footprint. So depending on, what is the energy supply at this remote location, how is the legislation changing for that particular country that you're operating in, and what are the demands with regards to decarbonization efforts and other sustainability initiatives. It might be required that, new technology needs to be installed in order for them to continue that operation. So after, doing a high level analysis, looking at different alternatives, maybe microwaves might be the only option for some particular mine sites.
Mm, yeah.
Yeah.
And speaking of, you mentioned new technology of microwave, right? So where do you see solid state microwave technology taking the mining industry over the next decade?
To answer that question, I would just start by saying I would like to see it at many mine sites in the next 5 to 10 years. I'm not sure of which sites are currently um, using it. As we mentioned with NDA, They want to keep this to themselves until they're protected and they're more confident in their process. But I think it's just inevitable. Like, I don't see any other technology where there's been so much research in the last 30 years, and even within the last 2 calendar years, the number of papers that are coming out, the number of work on piloting efforts has substantially increased. So I can only see the interest in microwaves in mining continuing. I'm not sure, but rate is going to continue, but it's just a matter of time before we see an installation.
Mm.
Yeah, I think, specifically to solid state and how it's the source using your solid state power to run these processes. The advantage of using solid state is that it can be uniquely hardened and built to sustain or be able to be operating in these environments. You look at the transition from other vacuum tubes in other industries to solid state, namely, space or other very demanding military applications where the existing technology in tubes wouldn't couldn't be sustained or couldn't be ruggedized to be usable in those industries. Solid state in the industrial side is uniquely positioned to be able to handle those rugged demands and low maintenance requirements of that the mining industry requires.
Mhm. And Adam, if a company is looking to consider solid state technology, what would be the first steps you recommend for them to explore the feasibility of such a process?
So we're at Crescend. We have a microwave development lab in Ankeny, Iowa, and we've developed a microwave solution success journey program where we're able to share this with anybody that's interested. But we have the ability to go through all the steps with a customer and determine the feasibility of using microwave power in a particular process, whether it be drying, heating, or comminution. We have dedicated applicators that are they're lab scaled applicators, but what we use these for is to uh, develop the engineering parameters and characteristics of the particular material of the process in order to start to build the estimating model on how a system might look in a larger scale, either pilot or commercial scale situation. We're able to take that engineering input data that we realize and capture in the microwave lab and use that in simulation work that we do to scale and to verify that the process works. This is invaluable to do a lot of work prior to investing significant money in a pilot scale physical system. This is obviously common. These simulation tools are commonly used in many microwave applications where it is really advanced in the last 20 years to be very accurate and predict what the results of the process will be. Um, and so it de-risks the process so you can invest just the right amount of money to your point where you have a successful um, opportunity in front of you to execute on a larger scale system.
Yeah, I think that testing process is important 'cause it goes back to, I think, with the first question we talked about with you, John, was that you had mentioned in other applications and other use of microwave technology is dependent upon different types of minerals and how they react to the microwaves. So that's part of the testing process that's done early on at the test lab here at Crescend. Is that right, Adam?
Yeah, that's correct. You need to do the validation to capture that data to know how much power is needed to raise the temperature or do whatever variable you're looking to for the end result. If it's a significant amount of macro and micro cracking in the combination process, or you're looking to achieve a certain temperature in a reduction process, those things we have all the instrumentate. All of our systems are instrumented to be able to capture this. We can record this via video on the computer, and then this can all be shared in the with the team that's working on the project.
All right. Thank you, Adam. So, Jon, any other last thoughts or comments you wanted to make?
I could spend hours talking about this. I'm just grateful for the opportunity to speak with both you, Lori, and Adam about the future of solid state in the mining industry. I would say I'm very excited about what's going to happen. I'm going to keep reading the literature. I'm looking forward to that first installation, if it doesn't exist already. I really think there's a lot of potential here.
Thank you so much for sharing your work with us and your expertise today. It's been a pleasure, Jon. Thank you. And thanks, Adam, for joining us today as well on the interview.
All right. Have a great day, Lori and Jon.
All right.
Thank you, Adam. Thank you, Lori.